Hello, and welcome to Agrosive Physics. Today is day 78, and what we're going to discuss today is what happens when a wave hits a boundary. Now, we talked about waves last class, and we discussed the different types of waves. We have a mechanical wave, which required a medium, electromagnetic waves, which do not, also known as light, and then we talked about the different types of waves, transverse, longitudinal, and surface. Now, ultimately, a wave is going to travel through a uniform medium, meaning that it's a medium that's constant throughout, at a specific speed. Ultimately, it will hit another material. In the case of sound waves, it may hit a wall, it may hit another fabric or something like that. Light will hit water, or it will hit glass, or maybe it will even go into a denser material from the vacuum of space, such as the Earth's atmosphere. Well, there are three things that happen every time a wave hits a new material, and those are reflection, refraction, and absorption. Now, reflection is when a wave bounces off the material. Refraction is when a wave enters the new material and changes its speed. And absorption is when it hits the boundary and loses some of its energy. So some of the energy is lost. Ultimately, sound waves, as they travel through a room, will bounce off of different things, but eventually the sound waves will dissipate. You won't be able to continue to hear the sounds that you uttered earlier because the sound waves, as they hit new materials, will dissipate and some of that energy will be absorbed. Reflection is also known as an echo if we're talking about sound waves. So reflection is bouncing off the boundary. Refraction is going into it and changing the speed, and absorption is when it loses energy. Now, all three of these events occur every time a wave hits a new material. Some situations will be mostly reflection and a little bit of refraction and absorption, or ultimately it could be a lot of absorption and very little refraction or reflection. But no matter what, every time a wave hits a new material and hits a boundary between two materials, it will do those three things: reflection, refraction, and absorption. Now, reflection is bouncing off a material. And the amount of reflection that occurs is based on the density difference between the two materials. For example, if air is the material in which the sound wave is traveling and the sound wave hits a wall, well, the density difference between the air and a wall is going to be fairly high. The wall is very dense and the air is not. So in that case, most of the wave will be reflected. However, there will still be some of the wave that travels into the wall, and when it travels into the wall, some of the wave will be absorbed and will be lost in terms of its energy. So in that case, a higher density difference will make more reflection occur. If it's a smaller difference in density, for example, if sound wave is traveling through air and then all of a sudden hits a cloud, which might be slightly more dense, what will happen is the majority of the wave will be refracted into the new material, into the cloud in this case. Very little of the sound wave will be reflected. And then some may be absorbed, or a combination of the three. In all cases, the 100% of the three will be transferred between those three events. Some will be reflected, some will be refracted, and some will be absorbed. Now, the most important thing to realize about the reflected waves is that the frequency of the wave stays the same. We haven't talked much about frequency yet, and we're going to define it more in depth later on, but the frequency of a sound wave is also known as its pitch. When I speak into this room, what's happening is some of my sound waves are traveling through the room and hitting objects. The reflected sound waves don't sound any different than my original speech pattern. I don't sound like I have a higher pitched voice or a lower pitched voice when the sound waves are reflected. So the frequency, which is the pitch of my voice, stays constant for all of the waves that are reflected in the room. The speed of the wave is also the same. The speed of a wave is determined by the material in which it's traveling through. So when the sound wave is reflected into the room, it has the same frequency and it also is traveling at the same speed. So the speed of the wave is constant in a specific medium. In this case, if we're talking about air, the sound waves travel at a specific speed, and they hit objects, bounce back, they still have the same frequency and they still have the same speed. So reflection is a case where the wave will hit a boundary, bounce off, and the speed and frequency will stay the same. Now, depending upon whether or not you're going into a more dense or a less dense material will determine whether or not the wave flips over or stays in the same orientation. So we call this the orientation of the wave. For example, if we have a transverse wave and there's a crest traveling forward and it hits a more dense material, as it bounces back, instead of a crest, there will be a trough instead. If we have a compression that hits the wall, an expansion will be sent backwards. And that's the situation where you have a less dense to a more dense material. In this case, air to the wall, for example. Now, we have another term for a crest turning into a trough. We can use a degree, an amount of reflection, and that is 180 degrees. So a crest flipped over will invert 180 degrees from its original position and bounce off as a trough. On the other hand, if we go from a more dense to a less dense material, for example, if you knock on a door, the sound wave travels through the door, and when it gets to the other end, some of the sound wave goes into the air on the other side of the door. Well, the waves that are reflected back into the door, and it may be a certain percentage out of 100 of the wave that is reflected, but it will come back with the same orientation. So if we go to less dense to more dense, the wave flips over. If it goes from more dense to less dense, it stays the same. So a wave traveling back into the door will, if it started as a crest, will stay a crest. The wave that bounces back, if it was a trough, it will stay a trough. If we have a compression that hits the new boundary, it will come back as a compression. If it's an expansion that hits the new material, it will come back as an expansion. So when we have waves reflect off a material, they could come back in the same orientation or inverted. And instead of inverted, we can call that 180 degrees. Now, we do have some analogies to help us visualize this. One is thinking of a slinky type wave, so a wave that is sent using a slinky, and it is fixed on one end. That simulates less to more dense. As the wave's traveling, it comes forward as a crest, let's say. When it hits the boundary, because it's fixed, the crest, that part of the wave that is hitting the wall, it's going to try to pull on that fixed point, almost like tying the slinky to the wall. When it pulls up on the fixed point, what's going to happen is Newton's third law is going to take over. Now, if you remember, Newton's third law is the law of every action has an equal and opposite reaction. So as the wave pulls up on the fixed point will pull down on the wave. So the slinky will pull up, but the wall, in this case, if we tie it to the wall, will pull down. Well, when it pulls down, it's going to take that crest and invert it. So the reflected wave will be reflected upside down. So because of Newton's third law, if we use that analogy, it will show what happens when a wave goes from a less to a more dense material. It will flip over. And if we think of Newton's third law, every action has an equal and opposite reaction, we can visualize what's happening. This is a good analogy, and it will allow us to visualize that, and hopefully we'll remember that when a wave hits a more dense material, it bounces back upside down. On the other hand, we could have a situation where it hits a less dense material. And in that case, we think of it as a spring that is not connected to anything, so it can move freely. Well, what's going to happen then is the wave's going to travel along, and this is the situation I spoke of before, where we have sound waves going in a door and then hits the edge boundary between the door and the air on the other side and bounces back with the same orientation. Well, at the end, where it's hitting the door between the door and the air on the other side, we can think of the spring not connected to the wall. Well, what's going to happen is the spring is going to lift up. The energy of that wave is going to pull on that last piece of the slinky, if we use the slinky as an analogy again, and nothing's going to stop it. So it's going to raise itself up. It's going to move it to a higher point. Well, when a wave moves to a higher point in this case, we can think of it as having more potential energy. And if we think about potential energy, now that end point of the slinky is at a higher point. Well, it's not at a natural state to be there, so it's going to release that energy. And when it releases that energy, it's going to send the wave back in the same format, in the same orientation. So a crest travels along, lifts that last edge of the slinky, rises up, and then sends another wave back as it comes back down to rest. So the potential energy stored at the end of the slinky will be released and send a wave back in the direction that it came. So the reflected wave in that case will have the same orientation. If I send a crest, the end of the slinky lifts up. When it's as high as it can go, it releases that energy and sends another crest back towards the original position. So the wave is reflected with the same orientation. A crest ends up being a crest again. So these are analogies to help us realize what happens in this case when a wave hits a less dense material from a more dense material. So if we have less to more dense, the wave flips over, similar to a Newton's third law situation. And when we go from more to less dense, it has the same orientation because it gains potential energy and then releases that energy. The second type of event that occurs other than reflection is refraction. And refraction is when a wave changes speed as it enters a new material. And the new density of the material will affect how much the speed changes. What's important to realize is that the refraction of sound waves going into a more dense material will actually speed up when it enters that new material because it's a material wave. It's a mechanical wave, and it needs a medium in which to travel through. So what happens for refraction of sound waves as it travels into a more dense material, it will actually go faster. And the reason that's the case is as the density of materials increases, it means that the particles inside the material are actually closely bound together. They're closer and tighter knit together. So they're able to send the wave through the material at a more rapid rate. The vibrations occur and send the wave more rapidly, and the speed will increase. Light, on the other hand, will actually slow down when it hits a more dense material. And that's because light traditionally can travel in a vacuum, and a vacuum has virtually no density at all. So when it hits a more dense material, light waves will actually be impeded by the new material and they'll slow down. So the speed of the wave will depend upon whether or not it's a mechanical or an electromagnetic wave. And remember, electromagnetic waves are also known as light waves. So when sound hits a more dense material, it speeds up, and when light hits a more dense material, it will actually slow down. The key is that the refraction is the change in speed. Whether or not it goes faster or slower doesn't affect the fact that it's refracted. Refracted just means a change in speed as a wave hits a new material. Now, sometimes waves will travel at an angle into the material. And when they travel at an angle into a new material, they'll actually turn because the wave is changing speed. If a wave travels directly into a new material, effectively perpendicular to the surface of the new boundary, they'll just speed up or slow down, but they'll travel in a straight line. If a wave is at an angle, it will actually turn a little bit. And when we talk about light, we'll be able to calculate it more readily. But for now, it will either turn closer to a normal line, which is perpendicular to the surface, or farther away. For now, what you need to know, though, is that refraction is when light enters a new material and changes speed. Refraction of light is the reason that we see, if we look into a pool from a deck, the water looks more shallow than it actually is. It's also why the sunset appears to be still setting when the reality is the sun has already passed the horizon. We're able to see the sunlight longer than we should because some of the light is turned when it enters the Earth's atmosphere and then travels in a straight line towards our eyes. So refraction in this case is just the change in speed. Sometimes it will travel straight through, and if it hits at an angle, it will turn either closer to a normal line or farther away. Now, the third thing that occurs at a boundary is absorption. And that will depend upon how much energy is dissipated when the collision occurs between the wave and the boundary. And in some cases, the density difference will matter, and in some cases, you will have more or less absorption depending upon the situation. But if you recall, there are three things that occur at every single boundary. You have reflection, which is when the wave bounces off. You have refraction, which is when the wave goes into the new material and changes speed. And you have absorption, which is when the wave loses energy when it enters the new material. This was day 78 of Aggressive Physics, and I thank you. Waves will eventually hit a boundary as they're traveling, and the boundary will exist between two different media. It could be air versus a wall. It could be air versus a thicker, denser part of the air, maybe a cloud or something like that. It could be a wave traveling through water and then hits a piece of glass. There's all different types of boundaries, but there are three things that occur at every boundary. We have reflection, which is where it bounces off. We have refraction, and that's where it changes speed. And the change in speed will be in the new material. Finally, we have absorption. And when a wave is absorbed, it loses energy. Now, all three of these things occur, but depending upon the density difference, you may get more reflection, more refraction, or more absorption. For example, if a wave hits a soundproofing material, maybe made of foam or something like that, perhaps you get more absorption, very little reflection. The shape of the soundproofing may also cause the reflection to hit a new piece of the same soundproofing, thereby causing a new set of conditions here. And then you have more absorption again. So if you set up a boundary that looks like the egg crates that you'd have on a bed, this would create reflection that would cause more absorption. That would be the general byproduct. If you wanted the sound to bounce off, you'd make a really dense material, not foam, and maybe you'd get predominantly reflection. Anytime part of the wave goes into the new material, though, it will refract, and refract is just a fancy word for changing speed. So the delta speed is what refraction is about. We're going to have specific values that we can calculate refraction, specific values that we can calculate for reflection when we do our next unit. But for this unit, it's mostly terminology, and the terms are reflection, where it bounces off or rebounds, refraction, where it changes speed in the new material, and absorption, when it loses energy. Thank you. When we deal with a wave bouncing off of a boundary due to reflection, there are two cases. We can go from less to more dense. In that case, it acts as if you had a spring that was tied down to a wall. So if this is the wall and this is the spring, what would happen is we have the spring connected here. If we were to send a wave down the length of the spring, either a longitudinal or a transverse wave, the reflected wave is inverted. So, if we're sending a longitudinal wave, we have a compression. All of the coils in the spring, for example, would push together, compress, compress, compress. As it gets to this point, it will compress against the wall. Well, Newton's third law says every action there's an equal and opposite reaction. So we have third law. Action, reaction. So the wall doesn't like getting pushed around, so it's going to push back. And instead of a compression at the wall, the resulting wave going backwards is going to be an expansion. So we would have compression in and expansion out. If we had a transverse wave, it would look a little different. As I send a crest to the left here, what's going to happen is each particle is going to get pulled upward as the wave travels. This is almost a time-lapse photography here. As it pulls on this point that's tied down, and remember, this is going to be an analogy. This is a simulation of what happens when a wave hits a more dense material. But it's as if this string is tied to the wall. It's going to pull up at this point. Newton's third law again. The wave is pulling up on the wall. The wall doesn't like it. So what happens is the wall is going to push down on the resulting wave. So as the wave pushes down, it's going to send a trough backwards. So each of the times this crest pulls up on the wall, it's going to retaliate, if you will, and it's going to send a trough in this case, going backwards. We have the crest, which is upward. We have a trough, which is pointing down. This would be a single pulse we're sending. We could send a continual wave train, and that's going to be a topic for later. What we'll end up creating, spoiler alert, we'll create a standing wave. But for now, this is when we go from a less to a more dense material. All right, on the other hand, waves can go from a more to a less dense material. Three things happen at every boundary. We have reflection, refraction, and absorption. So when we go from a more to less dense material, any of the waves that are reflected with the same orientation. So the reflected wave has the same orientation. A simulation for this is a spring or a string that's not connected to a wall that can be allowed to move. So here's what happens. We'll just do a string in this case. What I'm going to do is I'm going to send a crest along a string. Maybe it's a thick rope because it's hard to imagine sending a wave down a really thin string without it being tied to something. But if I send the wave, maybe a thick rope, we're going to get to a point where that crest is going to continue along and get to the end point. We'll say that that's the end point right there. Well, each of the pieces of this wave, each of the particles, they're going to pull up on this single point. Well, that point does not retaliate. That point can be brought to a higher place. And each of the pulls is going to cause it to go higher and higher and higher and higher. Well, ultimately, we'll end up with a situation where we have the big rope, and then the end of the string or rope is at a very high point. Well, at this point, it has potential energy. And that energy is going to be released. It's almost like an electron in a higher energy level. It's not stable. So that point right here is going to release that energy. And as it releases the energy, it's going to pull down and send a pulse back in the other direction that has the same orientation. So as that drops, you'll end up with a crest that'll send back. So as this lowers, you end up with a flat line, and the crest will return. So a crest comes in, lifts this point up to a higher potential energy. That potential energy is released and sends a wave back in the direction where it came from. So this is an analogy for when a wave hits a boundary of a less dense material from a more dense material. And we use potential energy as the analogy. I'm going to simulate reflection into a more dense material. And if you remember, the reflected wave is inverted. So my hand holding this end, as I send the pulse down, you'll notice that on the way back, I send a crest, and a trough comes back. And that's because of Newton's third law. At the end point, what's happening over here, we have the wave coming along. It's pulling up on this point, And Newton's third law says every action has an equal and opposite reaction. It'll push it down. And what we end up getting is an inverted wave. So a crest comes down and a trough comes back. The effect of that is we'll end up getting interference. We'll talk about that a little later. So this is reflection from a less to a more dense material.